Hi everyone, my name is Wang. Today I'm going to present our paper called Neural Network-Based Reconstruction in Compressed Sensing MRI without fully sampled training data. And the authors are myself, Adrian Dalca, and Mert Sabuncu. A little bit of background on the problem domain that we're working with. We are in the domain of compressed sensing MRI, which takes measurements Y and Rm, which are the results of a forward operator F omega performed on true images X and Rn, where M is less than N. And F omega is the undersampled Fourier operator. We wish to find a reconstruction of the true image X hat. So in this block diagram, we see that X has been transformed by a forward operator into measurements Y, which we observe. And we want to do some type of post-processing on the measurements in order to get out a reconstruction X hat. In classical optimization, what we typically do is perform an iterative optimization procedure and introduce a regularization function R, which restricts the set of permissible solutions to our minimization algorithm. Two things that I note is that this method requires no fully sampled data. Even though it's not a machine learning algorithm, and even though it's not done over a training set, it's quote unquote unsupervised because it only takes in a single instance-based undersampled measurement Y at a time. And additionally, it's robust because it's independent of a training set or any ground truth images. Alternatively, another method that we have is supervised reconstruction, which takes a data set of undersampled measurements and fully sampled images, which are paired, and tries to learn an optimal parameters theta star of a mapping, which I call G theta, which maps from undersampled measurements to reconstructions. And here's an example of a supervised formulation. You can see that this is dependent on lots of fully sampled images. Here we see X as an input into the loss function. So a lot of fully sampled images may not be available in the clinical setting. And additionally, this has been shown not to be robust to dataset shifts or noisy perturbations. So here's the main idea of our paper. We want to combine the unsupervised nature of classical optimization loss with the performance of supervised methods. So let xi hat be the output of some learned neural network G theta. Equation 1 is the classical loss that I outlined before. Equation 2 is the supervised loss that I outlined before. And equation 3 is the unsupervised loss that we propose. Basically, we perform the classical loss for every input, for every measurement in our data set. So it's done over entire data set, and for every data set, we pass it through a neural network G theta, which we see here, xi hat. And that neural network learns to perform the classical optimization for every element in the data set. So you can see that this is kind of an amortized optimization over the data set because we are training the network G theta to minimize this algorithm, this classical loss, for every single element in the data set. And in that way, we eliminate any dependency on the ground truth images X. So just to be explicit, here we have our forward model, the measurements yi, which are passed through G theta, and we get a reconstruction xi hat. In supervised reconstruction, the loss L sup has a dependency on the ground truth images. But in our unsupervised reconstruction case, we don't have that dependency. We lose that dependency. Furthermore, in order to improve our loss function and take inspiration from classical optimization schemes and also supervised unrolled architectures, we introduce a new model architecture, which I'll outline here. So first, I'll talk about half quadratic splitting, which is a very popular optimization scheme for the classical loss function that I outlined here. Basically, what half quadratic splitting does is it does an iterative decoupled optimization. So here I denote two iterative minimization schemes that are performed iteratively and alternating. So the first step I call reg, and the second step I call DC. In the reg step, we get an intermediate value zk, where k indexes over the iterations. And this minimizes the regularization plus some coupling term, where xk is the output of the previous iteration. And in the DC step, we get an output xk plus 1, which is done by minimizing the DC term plus some coupling term, just as before. And here lambda is a hyperparameter. So broadly, what we see is that given an input y, we perform an alternating minimization of the blocks reg, DC, until convergence or until some criteria has been met. So what we propose is what we call hqsnet. So given our unsupervised loss function here, that I introduced before. What we do is we replace the reg step with a CNN architecture, and we solve the DC step in closed form. So here I've copied over the same two alternating minimization steps as before, where here the reg step has been replaced by a CNN, which I call little g of theta. You can see g of theta as basically learning the proximal operator for the reg step from before. And additionally, x hat k plus 1 denotes the closed form solution for the DC step, where the hat denotes the Fourier transform. So again, what we see is that given an input measurement y, we pass it through a CNN g theta. We pass it through a CNN g theta 1. Then we solve the closed form DC solution. Then we pass it through another CNN g theta 2, perform another closed form DC solution, and do that iteratively for a set number of iterations, capital K, until we get our output, capital G of theta. So just to be explicit, here our model architecture for hqsnet is that we get, given our measurements yi, we pass it through a CNN, a DC, CNN, DC, iteratively for an unrolled number of iterations. So you can see that this is similar to unrolled architectures in supervised settings, but to our knowledge, this is the first time that it has been done in an unsupervised setting. So what we've done is we replaced an expensive iterative optimization scheme for the classical setting with a simple forward pass of a neural network. So whereas before HQS by itself would require many optimization, alternating minimization schemes for every input measurement y, now we've trained on a set of measurements. So our network G theta will be able to perform the optimization almost instantaneously for a single forward pass of the network. Additionally, we see that we can show that our method has superior performance under noisy conditions compared to supervised models. And lastly, since the function g theta is tasked with estimating the reconstruction for any viable input measurement y, and not just a single instance, amortized optimization has been shown to act as a natural regularizer for the optimization problem. And that's something that we can see in our results as well. So here are some results. What we do is we compare performance of HQS, hqsnet, which is our model, and a cascade-net, which is supervised baseline model. HQS and hqsnet minimize the same loss with the same hyperparameters, and the regularization function that we use is a total variation plus L1 wavelet sparsity. HQSnet and cascade-net models have the same number of unrolled iterations and the same type of CNN architecture. And additionally, the data sets that we use are T1 weighted brains, T2 weighted brains, and PD weighted meats. So firstly, I want to outline the runtime analysis and the performance boost we get from runtime with our HQSnet model. So because HQSnet only requires a single forward pass of a neural network instead of explicitly solving a optimization scheme every single time, we see that HQSnet performs massively better while achieving the same loss. Note that this loss is calculated over the test set, not over the training set. Here is a representative slice of our model compared to the ground truth, HQS, and cascade-net. So we see that HQSnet performs admirably in terms of PSNR compared to HQS, and cascade-net here is a upper bound baseline. And our HQSnet requires no access to fully sampled ground truth. Here is a box and whisker, a box plot of our three comparison models. So left side of each is 4-fold acceleration rates, and the right side is 8-fold acceleration rates. So we see that HQSnet performs admirably, sometimes outperforming HQS, especially in high acceleration rate settings. And we also outline for all three data sets that we tested on. Here is the experiment for noise robustness. So we see that for cascade-net, once we introduce a little bit of noise, the reconstructions get destroyed, whereas our HQSnet can kind of go around that. And we think that this is because of our lack of dependency on fully sampled ground truth. And here is a more comprehensive experiment where we perform reconstructions on many different noise standard deviation settings for Gaussian noise, additive Gaussian noise. And in the top row here, we introduce noise in the image space, and in the bottom, we introduce noise in K space. So we can see that in all settings, our hqsnet outperforms cascadenet for all noise scenarios. Here are some references. Thank you very much for your time.